This is Chun Huang, and I'm from School of Mathematics, Southeast University, Nanjing, China. The topic of my presentation today is stability analysis of Quaternion-valued neural networks with leakage delay and additive time-varying delays. I will provide my presentation from the following four aspects. Firstly, let me show you some background information of this research. In the past decades, real-valued neural networks have been successfully applied in secure communication, information processing, engineer optimization, automatic control engineering, and some many other areas. However, RVNs have their own limitations, such as the detection of symmetry problem cannot be resolved by a real-value neuron, while it can be well solved by a complex-value neuron. Therefore, the performance of complex-value neural networks is more preferable than that of RVNs in practical application with complex signals. During the last few years, it has drawn considerable attention to the dynamics of complex-value neural networks, and there have been lots of significant results associated with such kind of topics. The quaternions are members of a non-commutative division algebra. Some operation laws, such as the commutativity of multiplication, are not yet applicable for quaternions, which is quite different from the real or complex numbers. Owing to this difficulty, the research of quaternion had almost remained stagnant for a long period of time. Recently, the resurgence of the study for quaternion system is underway, and an increasing spectrum of applications based on quaternions are found in quantum mechanics, attitude control, computer graphics, and signal processing. It has been proven that neural networks, along with quaternion, possess better performances and wider applications than both RVNs and CVNNs. Actually, the three-dimensional and four-dimensional data can be expressed as an entirety, which is more authentic and reliable in modeling of practical application. And Quaternion-valued neural networks emerge at the right moment. It is well known that time delays are inevitable in neural systems owing to the limited propagation velocity between different neurons. Dynamical behaviors of neural networks could become more complicated, and it may result in performance degradation, such as instability, oscillation, bifurcation, and so forth. Usually, the time delay in the state is supposed to appear in a singular form. Nevertheless, it has been demonstrated that signal transmissions may experience a few segments of networks in several practical situations, and the different conditions of network transmission probably result in successive delays with different properties. To the best of our knowledge, up to now, few scholars have taken the stability problem of quaternion-valued neural networks with additive time-varying delays into consideration, which motivates our research. Okay, next is the main results of our research. First is some preliminaries about Quaternion algebra. The quaternion is an extension of the complex number, and the quaternion can be described in the following form: m equals m0 plus m1i plus m2j plus m3k. The quaternion imaginary units I, j, k obey the following rules. It is worth mentioning that ij equals minus ji, from which one can note that the quaternion multiplication is not commutative. We proceed to introduce some basic operations of Quaternion algebra. For two quaternions m and n, the sum and product of M and N are defined as follows. In addition, the conjugate transpose of M and the modulus of M are also defined. Next is the model formulation of the research. Consider the following Quaternion-valued neural networks with both leakage delay and additive time-varying delays, as shown in System 1, where YT denotes the state vector. C is a positive diagonal matrix and it represents the self-feedback connection weight matrix. A and B are the interconnection matrices, which stand for the weight coefficients of the neurons. G represents the neuron activation function at time t, and H denotes the external input vector. Delta is referred to as the leakage delay, which satisfies delta is greater than or equal to 0. D1t and D2t represent the two delay components in a state. In order to simplify the model, we assume that Y star is an equilibrium point for system 1. By applying the transformation xt equals yt minus Y star, system 1 is further converted to system 2. Next is two assumptions throughout this paper. Assumption 1 is about the delay components in the state D1t and D2t. It is assumed that D1t and D2t are continuous functions and satisfy it has lower and upper bounds, and the dots of D1t and D2t also have upper bounds. Assumption 2 is about the activation function. It is assumed that the activation function satisfies the Lipschitz condition, as shown in assumption 2. What follows is some lemmas, which are very instrumental throughout this paper. From lemma 2.1, we can see that according to the property phi, any quaternion matrix A can be uniquely expressed as A equals A1 plus A2J, where A1 and A2 are complex valued matrices. Lemma 2.2 is about the conjugate of quaternion matrix and the multiplication of quaternion matrices. Lemma 2.3 is very important. Let A be a emission matrix and A equals A1 plus A2J. Then A is less than 0 is equivalent to the following matrix is less than 0. Lemma 2.3 reveals the equivalence between the negative definiteness of n times n quaternion matrix and the negative definiteness of a 2n times 2n complex value matrix. Lemma 2.4 is Whittinger inequality in the quaternion domain. Suppose M is a positive definite emission matrix and omega s is a vector valued function. If the integrations concerned are well defined, then we have the following inequality. Lemma 2.5 is very important. It is the alleged reciprocally convex inequality in the quaternion domain. For any vector Xi belongs to quaternion domain, a positive emission matrix P and the matrices omega 1 and omega 2 Define the function C alpha p as shown in this expression. If there exists a matrix X satisfying this matrix is greater than or equal to 0, then we have the final inequality. It is a large reciprocally convex inequality in the Quaternion domain, which is very important in our proof procedure. Next, we present the main results of this research as shown in theorem 3.1. Suppose assumptions 1 and 2 hold. If there exist positive diagonal matrices M1, M2, M3, positive definite matrices P, Q, R1, R2, and appropriate matrices U, V, S1, S2, such as the following three Quaternion-valued LMIs hold. Then the Quaternion-valued neural network is globally asymptotically stable. The explicit expression of omega ij is shown as follows. Next, we show the sketch of the proof. Construct the following LyapunovKrasovskii functional as shown in 6. And then the derivatives of Vi can be calculated and estimated straightforwardly. Where lemma 2.4 has been applied in the estimate of the dot of V2t in 12. Based on lemma 2.5, we further estimate the two integration terms in the dot of V4t as follows. In addition, it follows from assumption 1 that expression of the inequality 17 to 19 hold. By applying the free weighting matrix method, we gather from 3 and we obtain the equality 20. Therefore, it follows from 11 to 19 and 22 that the dot of Vt is less than or equal to the conjugate of eta t times omega times eta t. Then it follows from 5 and 23 that the dot of Vt is less than 0, which together with the radial unboundedness of Vt guarantee the global asymptotic stability of the QVNNs2. The proof is completed. Next, we give the corollary 3.1. Suppose assumptions 1 and 2 hold, the equilibrium of system 2 is globally asymptotically stable if there exist positive diagonal matrices M1, M2, M3, omission matrices P1, Q1, school symmetry matrices P2, Q2, and some appropriate matrices belongs to the complex domain, such that the following complex valued LMIs hold. Okay. Next is we will show an illustrative example to validate the effectiveness of the theoretical results. Consider the two-dimensional QVNNs2 with parameters given as follows. In accordance with remark 2.1, the Quaternion-valued matrices A and B can be uniquely expressed as A equals A1 plus A2j and B equals B1 plus B2j, respectively, where the explicit expression of A1, A2, B1, B2 are given. In addition, it can be readily verified that assumptions 1 and 2 are all satisfied. Therefore, a set of feasible solutions to CVLMIs 24 to 25 can be established by the Yalmip toolbox in MATLAB. Here, only partial matrices in the solutions are listed due to the limited space. Therefore, the equilibrium of the QVNS2 is globally asymptotically stable according to corollary 3.1. And figure 1 depicts the transient behavior of the neuron state in QVNS2. At last, we will draw the conclusion of this paper. This paper is concerned with the stability analysis of Quaternion-valued neural networks with both leakage delay and additive time-varying delays. Based on the Lyapunov functional method and inequality technique, some delay-dependent criteria are provided by fully considering the relationship between time-varying delays and upper bounds of delays. It is worth mentioning that the stability criteria are established in two forms, in which CVLMIs can be directly resolved by the Yalmip toolbox in MATLAB. That's all. Thank you for your attention. Any questions or problems is welcome.